Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 7th, 2025, so just yesterday. This paper introduces a new fine-tuning method that gives an average performance gain of plus 15.66 points on one model, which is nearly 5.9 times larger than the standard approach. The paper is titled, On the Generalization of SFT, a Reinforcement Learning Perspective with Reward Rectification, and the authors propose a remarkably simple fix for a deep-rooted problem. They show that standard supervised fine-tuning, a common method for adapting models by training them on expert examples, actually has a flawed reward structure that hurts its performance, and they fix it with a new technique they call dynamic fine-tuning. Also, the authors share their implementation on GitHub. You'll find the complete setup there, including the training and evaluation scripts, data preparation steps, and even their model checkpoints. It's all there for you to get started and reproduce their results. Okay, so moving to the results. This table lays out the performance of 5 different models on several challenging math benchmarks. For each model, we see 3 rows. The base model, the model after standard supervised fine-tuning, and the model after their new dynamic fine-tuning. The pattern is incredibly clear. In every single case, dynamic fine-tuning achieves the highest average score. For example, with the QN 2.57B model, the average jumps from 23.62 with standard fine-tuning to over 37 with dynamic fine-tuning. Building on those results, these plots show us how the training actually unfolds over time for the QN 2.5 Math 1.5B model. Across all of these different math benchmarks, you see the same story. The red line, representing dynamic fine-tuning, shoots up very quickly and maintains a high level of accuracy. In contrast, the blue line for standard supervised fine-tuning learns much more slowly and just plateaus at a lower performance. The final plot on the bottom right really summarizes this overall average trend perfectly. So we've seen that dynamic fine-tuning beats the standard method, but how does it stack up against other advanced techniques? Well, this table pits it against a concurrent work, another fine-tuning method called IWSFT, and the results are just as impressive. In most cases, dynamic fine-tuning delivers a stronger performance. For example, with the Llama 3.23B model, the average score more than doubles, jumping from 2.26 to 4.65. This pattern holds true across most model families, really underscoring the power of this approach. Okay, so the authors then test their method in a full reinforcement learning setting. This table compares dynamic fine-tuning against several other techniques, including offline methods, which learn from a fixed dataset, and online methods like PPO and GRPO, which learn by interacting with an environment. The key takeaway is right here on the bottom line. Dynamic fine-tuning, used in a simple offline setup, achieves the highest average score of 35.43, outperforming all other approaches, even the more complex online ones. This result is pretty remarkable. Alright, so what's happening under the hood to make dynamic fine-tuning so effective? This next chart is really revealing. It shows the probability distribution for individual tokens. You can think of these as words or parts of words. Most other methods, like standard supervised fine-tuning, tend to just make the model more confident about everything across the board. But look at the dark blue bars for dynamic fine-tuning. It creates this polarizing bimodal distribution, meaning it has 2 peaks. It dramatically boosts the probability of some tokens while actively suppressing others. So this polarizing effect is what gives dynamic fine-tuning its power, but is the method sensitive to the training setup? Well, these charts put that to the test. The one on the left varies the learning rate, while the one on the right changes the batch size. In every single scenario, the orange bars representing dynamic fine-tuning consistently outperform the blue bars for standard supervised fine-tuning. This demonstrates that the approach is really robust and not just a fluke of one specific set of training parameters. So, to wrap things up, the key takeaway is that a simple, theoretically grounded change to supervised fine-tuning can lead to huge improvements. By fixing a subtle flaw in how the model learns, dynamic fine-tuning dramatically boosts performance across the board. That's it for this episode.